Hello, this video is on a concept and the methods of computing the greatest common divisor of a pair of natural numbers. So first, what is to be a common divisor for a pair of natural numbers? What is to be a divisor? Let's start with warming up on that. So a divisor of d of a number n, or a statement that d divides n, is an abbreviation if and only if n can be written as a multiple of d, so it is d times something else, so u, for some natural number u. And kind of a quick observation that if n is a natural number, then there's only finitely many such possible divisors, because the divisor will have to be less or equal than n. Well, we can also assume that d is a natural number, otherwise we will have infinitely many things which are less, but still finitely many divisors. And a common divisor now of a pair of numbers a and b, well, it's just what it says. So it will be divisor, so that is d, a divisor of both. Let's now do something. So we are eventually to come up with the greatest such, with the largest such, and moreover it will be such that all divisors will divide it, which is more or less logically inevitable. But it's not totally logically clear why it should exist. Just by looking at the conditions it should satisfy, so it should be a common divisor. Why there is a largest at all? Maybe there is a largest in absolute sense, but not in the division sense. So yeah, I said that it's logically inevitable, but why couldn't it be that just two divisors which do not divide each other, and they will be hence incomparable, and the largest will be only in absolute value sense? So let's do some trick. Let's look at the totality of all common divisors. Just divisors of one number are forming a finite set. So if we take two numbers, still common divisors will form a finite set. So let's just denote this by a, b, with these double brackets around, so that will be the set of common divisors of a and b. And now what I'm going to do, I'm going to argue that there is always an element in this set which will be the largest in the sense of division. So there will be just an element such that all other elements in the set will be dividing it. So for that I just need one simple property of this set. And the simple property will be saying the following. So if I just take a pair AB and do something with one of them, so assuming that A is not smaller than B, with any pair we can do such assumption by choosing the largest, and then take B out, still have a natural number, then these two sets are the same. So that is my statement. Well, let's justify it. Let's unpack what the statement is saying. So here I have common divisors of A and B. That's a notation. Here I have common divisors of A minus B and B. Again, just following the notation. So what I'm saying here is these two sets are the same. What have to construct is a procedure, an isomorphism, so a way of going back and forth between the two sets, and these two back and forth ways have to undo each other. Well, it would be good to write elements of these sets in a more concrete way. So the first is just spelling out the words in division statements. So the first pair of conditions is that D divides A and D divides B. So here it will be some other divisor, but we use the same name, that D divides A minus B and D divides B. After all, I have to identify the sets. After all, I have to say that they are equal. Yeah, literally equal, I said. An isomorphism was not correct. It should be just equal as the totality of numbers. So here are the conditions determining D as an element in the first and in the second set. It would be good to spell these conditions out more. Just write them in equation form. So A is equal to D times something, and at the same time B is equal to D times something else. That are these two division statements written in an equational form. On this side I will have to write A minus B as D times, I will call it U prime, because now I have to really introduce a different letter. And B is equal to, I will use V prime, although it will be the same as V. So now I have to argue that if I have D satisfying these two equations, and D will have to satisfy these two equations with a different, perhaps U prime and V prime. So how to go from U and V, knowing that D divides A and divides B, to U prime and V prime? Well, that is given by two answers, two formulae. So U, in this case, you could see what it should be. This multiple for D, which will make D a divisor of A minus B, can be obtained from taking these equations and taking their difference. So U prime is U minus V, V prime is just V. And that is a recipe of how to start with these two conditions and turn them into these two conditions. It's effectively it's just saying that if D divides A and divides B, then D divides A minus B and B. So I want to now undo it and now produce the answers for U and for V if I know my U prime and V prime. Now if I know that D divides A minus B, so I know this U prime, and I know that D divides just B, I know this V prime. Taking the sum is what will give me U. So U prime plus V prime will be the answer for U, and V will be just the old V prime. And again, it's a procedure which justifies that if D is a divisor of A minus B and B, it will have to be a divisor of A and B. So I proved that these two sets of common divisors are the same. What am I going to do with it now? Well, I'm going to use it again and again and again. I'm going to technical term run it inductively. I will start with what I need to what I'm given, a pair of numbers, and then the task is to find all common divisors and maybe look for this greatest thing if it exists. In the process of doing this induction, I will see it inevitably that it should exist. Because what can I do now using this simple property? I can assume that A is not smaller than B and take B out of it, and then take it again if it's still larger than B, and take it again and take it again, take it as many times as necessary for that to become less than B. So that is nothing but Euclid's division. I'm replacing A by its remainder with the division of B on B, and now when I do that, R is less than B, and so I can run it again with B in place of A, so taking copies of R out of B and reducing it below R. So each time I do that, I will replace a larger number by something which is smaller than the other number, So I'm overall reducing the size of this pair, so to speak, and I cannot do it forever because I'm using only natural numbers. I have to stop. So how can I stop? I can only stop running out of one of the numbers, so creating 0. And then the other number, I'll call it D, and I'm claiming that that is a common divisor, and that is the greatest common divisor of the pair, because what is the set of these common divisors of a pair 0 and D? Everything divides 0, so the condition is just that this is the set of divisors of D. So all of the numbers in this set, by the definition, common divisors of a pair 0D, all the elements in this set are divisors of D. So D will be the greatest in the division sense. So that's a justification that for any pair of numbers there is the greatest common divisor. And the notation for this greatest common divisor will be just a single bracket. So this is D, now greatest common divisor of A and B. So we argue that it exists, and we actually have a process of computing it, which is called Euclid's algorithm. Take a pair and then reduce a larger by the smaller using the Euclid's division, replace by a remainder, and continue until you end up with a pair 0 and something. So in the next video we will implement it with a concrete pair of numbers and even do something more with it. Stay tuned.